So thank you for coming on this beautiful late afternoon. As usual, I will begin with a review, but maybe in this review some new remarks. Additional remarks. So if you walk over to Research 1 and you meet some professor over there, like Professor Keva, and he asks you, well, what have you been doing in this course? You just say, well, mathematically one thing that we learned about is if G is a group, we learned what the definition is and so on, but if G is a group, one of the most important things to understand is various kinds of group actions. And if it's a good professor, he will check you and he say, well, what's a group? And you will say, well, it's a set, and it's equipped with bilinear pairing, and a pair of GH is mapped to something we call G times H or G plus H, but we write it as G times H, and is associative, and so on. You have an inverse. And an action is the same thing. It's an associative action, and you assume that the identity acts trivially. So we studied this, and we studied various examples which were motivated by trying to understand the symmetries of a square. Simplest example we could think of. And so if the professor asks you, what do you mean? And you say, well, you go, anybody knows what a square is, and we're thinking of squares sitting inside some picture here. And this picture we talked about in several ways. It could be Euclidean two-space. Depends how you look at it. It could be affine two-space. Depends on how we look at it. As a set. It's a question what symmetries we have on this set. Symmetry being group action. And the professor, for example, Kevin, will say, well, that's great. You look at the symmetries, or what are symmetries? You say groups. The groups actually on this set are very important groups. And so the examples of the groups is the group of translations R2 plus, the translation group on A2. And then, because I try to make little things to remind you where we are, I'm always remind you that our base point is Crystal. She's down there now. It doesn't matter. That's a very good thing. Yeah, she was here, and now she's down there. That's good. You don't care where your base point is. Yeah. So if you choose a base point, then the R2 plus action of the base point, say the base point is called P0, of the base point gives you the affine space, at least as a set. That's the whole set. Because it's a free transitive action. Okay, Ron asks you, what does it mean transitive? It says, transitive means if you start at a point, any point, and somebody else gives you another point, you will find a transformation that goes from that point to that. It's transitive, it goes everywhere. And free means that there's only one of these transformations, or equivalently, that no transformation except the identity fixes a point. So this is a free transitive action. So you're learning some words, and you have good examples for your words. Free transitive action. And once we have determined a base point, 0 corresponds to the base point in the orbit. Of the translation group. So you choose a base point, and 0 corresponds to the orbit, and we're going to choose, in our case, the base point in the center of the square, just for fun, because we were motivated by this example, so I choose it there. Maybe I choose it some other place, it doesn't matter. So now we're in R2+. And then this is what we were talking about with several people. I remember talking about it with Maria in particular, the last lecture, is, well, and various other people. What are the symmetries, so it leads to a question, the symmetries of the affine space, which fix 0. I mean, we reduce to 0. I mean, given any point, we can translate it to 0 with the translation group. So we really care about what are those things which fix 0. Yeah. This is a project in understanding mathematics, which fix 0. That's a question. And then you say, well, what goes on in an affine space? You should always make pictures in my mind. Here's 0, and here's 0, and then we have all of these affine subspaces. It's a very good question by you. And what is an affine subspace? Well, it's completely clear. It's just an image, if you like, of an affine space, in this case of dimension 1, which is modeled on the vector space, one-dimensional vector space. So it's all these things through 0. I mean, there are other ones, of course, because there's no fixed point, but we're looking at the ones through 0. So we're left with the question, what transformations from R2 to R2 with T of 0 equals 0 preserve the lines, that's which preserve the affine structure. If you are asked about this course by a professional mathematician and you're able to tell this professional mathematician what I just said, that professional mathematician will say, you really have understood something. That's the way to say. I mean, you just get some technical stuff. We don't care about some technical stuff. You care about really what the structural stuff is that's relevant. And here it is. So we asked this question, and in fact, you can say you can call this, in some sense, an exercise, right? What are the transformations of preserved lines? I think in dimension 2 it's almost anything. This would be more or less my feeling. That's not true. It's not almost anything. But in order to claim that the transformation is linear, you need huge amount of additional structure in my mind. And I mentioned last time that in higher dimensions, if you preserve inclusion, you get the fundamental theorem of projective geometry. And if you're interested in this and anything around this, you can write a paper on that on this subject and make this your final exam. So solves the question: higher dimensions, higher dimensional analog of this question. Of this question. And really think deeply about it. I was just talking to somebody about a mutual friend of ours who is one of the greatest living mathematicians. He really thought deeply about this question in dimension 3 to really understand something deep. So simple questions quite often can really lead to deep thought. This is what we want to have, deep thinking. So this would be an interesting thing to think about. So this whole discussion leads to that. Now another thing that this whole discussion leads to this is that we take the linear transformations group of a vector space group linear transformation or linear transformation of the group of a vector space V is called or is denoted by GLV. GLV. General linear group of the vector space V. If the vector space is defined over a field R, that means it's linear with respect to the real numbers. If it's defined over the field C, it is linear with respect to complex numbers. It has nothing to do with which field it is defined for. In arithmetic considerations, it's defined over a completely different interesting field. So this linear transformation group, let us say, donated by GLV, right, acts as a group of affine transformations after choosing a crystal as a base point. I'm sorry, I won't bother you anymore. After choosing a base point, on the affine space A modeled on V. You just move the base point to 0 and then take the linear transformations. So we say that AF2, and that's now I'm getting to say AF2 over R, so this means over the two-dimensional real vector space. This is the group of symmetries. You can argue what this means, but it means that it preserves the affine structure, which means it preserves translations and it preserves subspaces and so on. Group of symmetries of A2. Right? That's everything you know that you can see. And you have to make that precise, but what I'm going to make it just say, well, you have the translations, R2 plus, bringing that to a point where crystal is. Oh no, I forgot, I would never say that again. And after that, you can apply transformations from GL to R. So, as we were talking yesterday with various people around here, a typical element of here might be T composed with small t in terms of the action of this group on affine space. This is acting as linear transformation. This is acting as a translation. So I'll write it here, acting linearly. Of course, you know what that means. After fixing the point, I won't belabor that anymore, and this is a translation. And now, if you're talking to my friend Kevin, or you're talking to anybody who does mathematics in a good way, they will say, "What do you mean, man, that this should be a group? How is this a group? How is the product of two groups a group?" So we learn an interesting question. How is the product of two groups let's say G1, G2, well, let's just write it, G1 times G2, a group. This isn't a reasonable question. Most of you would be too modest to ask that question because it looks too trivial, right? Because you would look at a simple example and you would say it's pretty trivial, it bores me, I'm not even going to think about this. You would probably say, well, let's look at R, which is an additive group. Let's say R, which as the additive group, well, I'll make it interesting. The product of the additive group, and now I'm going to take another group, I'm going to remove 0, from R, is, so you guys and girls who took analysis 1 know that R plus is a group, and you know that R with 0 removed is also a group, right? It's a very interesting thing. I had to remove 0 because you're really in big trouble by multiplying by 0, right? You don't know what the inverse is of multiplication by 0, right? Right? And you say, if you take an element here, maybe it's an element of R, let's put a pair here. So, I don't know, I'll call this element T for translation because I like to call it translation. And I'll put something here, I'll call this lambda because I'm thinking of multiplying by lambda, right? When I'm thinking of maybe dilating by 2 or something, I'm thinking about something, right? And I'm going to try to understand this thing as T times lambda. Trying to understand that. That's what I mean, multiply this. Yeah? Now we have an exercise that you should ask yourself. You say, I am a stupid beginner from Ho Chi Minh City. Yeah? You're lucky, because I am really an old guy who's supposed to know mathematics. But, yes? But you don't have to know anything. You just say, I'm stupid, I can ask any question I want. So we ask the exercise here. You say, if that's supposed to be a group, then what did I call the first thing? T. Then T1 times lambda 1 times T2 times lambda 2. What is it? What is it? Yeah?
T1 plus T2 times lambda.
I don't say, no, in this notation, I don't know whether it's called plus. Oh, if you want to call it plus?
Just because in the example you said plus, so.
Huh?
Just because you said plus in the example, that's it.
Yeah. No, I don't know. If I have T1 and T2, you might call it plus. Oh, I see what you're doing. I'm trying to understand what Maria means. Maybe she means this, T1 plus T2,
Yeah, that's fine.
lambda 1, lambda 2. Isn't that right?
Yeah.
Yeah, you're much smarter than I am. I'm slow. Well, you see, what I tried to write down, what I tried to say, Maria wanted to put a plus in here. I don't have a plus anywhere, I just have operations. This should be T1, T2, lambda 1, lambda 2. Fine. I hope that doesn't bother you. It's just T1 times T2, which is really plus. Yeah? Yeah? There's nothing wrong with that, is there? If you insist on what Maria wrote here, which is fine, I'm all right with it. But I want to really look at the operations in here. So that's when I write T1 next to T2, I mean plus. When I have lambda 1 next to lambda 2, I mean times. Okay? Please watch. What Maria told us to do is the following. T1, lambda 1 times T2, lambda 2 equals T1, T2 times T2 inverse, lambda 1, T2 times lambda 2. Isn't that not what she said to do? And now we know what T1, T2 means, and I know what lambda 2 means, and now I know what, I have to ask a mega question what that means, and then I maybe know how to multiply it. Right? So as you're led to a question of, if you believe any of this, you're led to the question, is T2 inverse lambda 1 T2 equal to lambda 1? Are you not led to that question? Isn't that exactly what's going on? Don't write this stuff plus and times, it's just an operation. Yeah? It's just an operation in the affine group. These two things are inside the affine group. The translations are in there, the multiplications are in there. That's GL1 if you don't mind. This is really the affine group in dimension. This is AF1. This is the stupidest thing you can think of. So you write some operation in AF1. You multiply two guys in AF1. And you know what it is. Maria told us what it was. She's right. But you want to know what it really means abstractly in terms of this. What it means abstractly is, well, you have to push the T2 through the lambda 1 to get it next to the T1, because that's the only way you know how to multiply T1, T2. So you push it through formally by putting T2 and T2 inverse here, and you get some guy in the middle that you want to do something about that should be lambda 1 if you believe Maria. Yeah.
So this only makes sense because you say that those two groups are subgroups of.
So right now, I'm talking about, it's very good, thank you very much. I'm talking about two subgroups of the big affine group. Yeah? And by the way, I'm talking about it here also. I just took a simple case, right? So what Mr. Weiss said is, I don't know if you could hear him, it's a really good point. I suppressed the point that I'm thinking about this as two subgroups. Say maybe, say G1 and G2 are subgroups of G. Just like an example, right? And it's good. It's good that if I had a nice systematic lecture, I would have said that myself, but I forgot to say it. It's good you pointed it out. Thank you. Okay. Question of that. And of course it's true, is it not? Is it not true that a dilation in dimension 1 commutes with the translation? I hope this is true. Yeah. Yeah. Okay. So it's fine, it's okay in dimension 1. Okay. So this is, we are about this. Let's do this is exercise 1. Let's do exercise 2 in dimension 2. So we have the affine group. Aff2 is of R. There are 2 groups in there. Let's dedicate this to Mr. Weiss. There's GL2R and R2 plus. Right? That's our idea. And we ask the question, why is that a group? Okay? Let's do it. Ready? Let's take T here, and we just use the notation here. T composed with T for a linear transformation, and small t for a translation. So linear, and small t for a translation, acting as a translation. Keep this in mind. We're talking about these guys in terms of their action on the affine group, on affine space. Okay. Here we go. You should write it down. If enough physicists here that say write it down. Do the computation. So you write it down. T1, T1 times T2, T2. So linear translation, that's our idea. Equals, do the same thing again. T1, T2, that's great. I know how to multiply T1 and T2, it's in a group. So then I have little T1 here. Then, oh no, I have to kill this T1, T2 because I molded it, I cheated and put it in there. Now I have to cheat it away. Oh, I'm already making a mistake. Let's see, no, it's good. Let's say T2, then T2 inverse. Yes, I didn't, now I'm good. T1, T2, times T2. Isn't this okay? Did I lie here? This is okay, right? Huh? And this is good. I'm good here. In the modern lingo of young people, I'm good here because I'm multiplying 2 guys in the linear group. That makes sense. Yes, I'm good here. I'm cool. So, but what about here? I have something here in the translation group, and something here I don't know what the devil it is. Right? So what I need here, I'm going to write this thing here as T1 as T1 hat, and I write the hope here. This is the way you do mathematics. I write the hope here that T1 hat times T2 is a translation. Because I really want this thing to be a group. I want the multiplication of 2 elements to be of the same form. You get it? Yeah? Okay? Well, let's just see what happens. Okay? So let's see the T, what the heck is this if you experiment with a vector? So let's see T2 of some vector, linear transformation of some vector, T1 of what that result, T2 inverse of this result. We have to see what that is, right? Have the courage to write it down. I'm looking at Deepak here. This guy's a physicist, a very good mathematician too. You would write this down, right? I know you. You would write it down. In the old days before you met me to make you think abstractly, you would just write it down, get the answer, and go to the next problem. Drink coffee and get donut. Right? What is this? This is equal to T2 inverse. Deepak would do this immediately. This is Deepak doing a calculation. It's a T2 of V plus T1. I'm doing the calculation that Maria told me to do. And now look at this wonderful thing. The T2 inverse kills the T2, and I have V plus T2 inverse T1. So, in big boy language, that says the conjugation, see I conjugated, this is a conjugation here. The conjugation the conjugation of a translation by a linear transformation is a translation. That's the key. Is that not the key? Because, you see, I don't care what this guy is. All I care about is a translation. Right? We need that fact. Okay? Okay? So in language of group theory, yeah? So if G1 and G2 are subgroups, as above, are subgroups of G and G1, G2, G1 inverse, so I'm conjugating it the other way around, it doesn't matter which way I do it, G1, G2, G inverse equals G2 hat in G2 for all G in G2 and G, then we say we don't have enough room to say it, so I'll write it on the next board. Well, I'll write it here, we have some room. You have two subgroups. This is the point of Mr. Weiss. This only makes sense if I really have some place where I know both groups are. And I want to say somehow that I've got really a product of groups, and I want to say here that a typical element of a product of a group is just T times lambda or T times whatever it is, T or whatever, G1 times G2. What you need for that thing to be a group, if that, then we say, if this works, then we say that G1 normalizes G2. This is the lingo in group theory. You have two groups, and I say, look, I'm talking about this all the time. We have two sets, two groups, you make a product. It's the fundamental first thing you do in any subject in mathematics. Be sure you have products of some kind, right? I mean, it's even something in fancy mathematics language. Yeah? That you have products. And you say a product of two groups is a group. That's absolutely wrong. Right? A product of a group is a group provided that the first group normalizes the second group. I mean, there's no special order. The second group could normalize the first group. I mean, what do you care? Right? That's all you need. And that's all we needed here. Because G1 normalizes G2. So the linear group normalizes R2. So we finished the discussion in that sense of the affine plane. So step one that we saw in our little project is to understand that the affine group of relevance, a two-dimensional affine group, or any affine group, let's make a general affine group, well, I don't care, two-dimensional affine group over the reals is the product of GL2 R, that's the linear stuff, with the translations, R2 plus, R2 plus, hi. With R2 plus, it's a product, and in mathematics you better symbolize which is the good guy and which is the bad guy here. It's not symmetric, not at all centric. Translations do not normalize linear transformations. Linear transformations normalize translations. So to emphasize that, we write a symbol here. Okay? So this is the symbol. This means the product where, in this case, GL2R normalizes the translation group R2 plus. Yeah.
And is this any different from saying that R2 plus is a normal subgroup?
Yes, it's different. It of course, because the product of these two groups is a full group, R2 plus is a normal subgroup.
Yeah.
But it's different. I mean, because you start with a group and ask what is its normalizer. So, Mr. Wise asked a very good question as usual. Let me just answer the question with a good definition, okay? So definition, if G is a group and H is a subgroup, then we introduce, this is maybe a definition and notation both at the same time. Then the normalizer of H and G, this is the set of G that normalizes it. These are the good guys. Oh, why don't I just write a set theoretically? Let me write it carefully, excuse me. The set of G in G, so that G normalizes H. Okay, that's what you really are hoping for with your transformations, so you can make this construction. This is called the normalizer subgroup. The normalizer of H in G, and it's pretty obvious. H is normal in its normalizer. That's what you're looking for. That's what you're looking for. So if I give Mr. Pham a group, and you want to see some good properties about this group, one of the first things you should see is what's its normalizer. Yeah? We were very lucky here. We start with a group of translations, and we find out that the normalizer is the first, this is the full group. Right? The normalizer is a full group, so let's write that here. If the normalizer is a full group, then we say that H is normal in G. Okay. So this is the whole thing, but the main thing you're interested in is this kind of construction. Because you're going to write products down and you want to multiply two products together. And so, look, every time you should think about what I just said. You write two products together, and you want to say that's a group. So you have to push through the T2 to the other side. The only question is whether the T2 conjugate of a translation is a translation. So the only question is, does the T2 normalize the translation group? Huh? Okay? That is the question. So I think that's enough of the abstract study. So example 2 then, our main example. Is this is the Euclidean group. So the Euclidean group, maybe I'll write it E2R, maybe sometime, I don't know, the Euclidean group, I will use this notation, Euclidean group of A2 of the affine plane equipped, well, of E, which is a set as the affine plane, equipped with the standard structure. Standard inner product. That's what we want to write down. We have seen last time, this is a group O2. In Germany, if you have a telephone, you can buy a contract from O2, maybe you don't. That's a company, O2. But here it means the orthogonal group. It means transformations which are orthogonal over the reals. And semi-direct product translations. Here you don't have to check anything because O2 is contained in the linear, so the O2R, where, let me write it here, well, where O2R is the group of linear isometries of R2 with the usual, with the standard bilinear form that I talked about yesterday. All review, which I'll write down again, bilinear form V1, W1. You can hardly read this here, I'm terribly sorry. VW equals V1, W1, V2, W2. O2 is already linear, so therefore it normalizes R2 plus. And it's a question of what in detail are the elements of O2 are? How do you understand them? I'm sorry, not here with my didactics. A little bit, well, let's move this up and let's start move back to work. Not very efficient. So how do we understand the linear isometries of the space equipped with its standard structure? Let me do it a little bit abstractly this time. Last time I gave you a strong motivation for what it should be. So let me write down the defining condition for O2. Usually you do not want to understand O2 with this condition, but I'm going to just write it down. It's very simple. Is that T is a linear transformation. I said it's in the linear group which preserves, so it's an isometry, it preserves the geometric structure of the Euclidean plane, which was given by the standard scalar product. T preserves the standard structure. You can write it in a technical way. It preserves the structure. It doesn't do anything to the structure for all V and W. In this case, in R2. It has to preserve the structure, right? I mean, if you're going to go blah blah in life, you just say it's going to preserve the structure. And then my colleague in mathematics says, what's the structure? And you say, hey, it's the more or less unique, standard, positive definite bilinear form on R2. That's the structure, that's it. My colleague in mathematics is very happy with you. That's great. Okay, what is that? How do you write that down? Well, we know how you write it down. It's okay. So Deepak in physics says, well, we do all this stuff. In physics, we want to do calculation. So what Deepak says is, if you write these vectors as column vectors, think these as column vectors, this is V transpose W. Is it not V transpose W? Maybe V is a row vector. So let's see here. I think V is a column vector, say V1, V2, and W is a column vector, W1, W2. And so V transpose W is V1, V2 times W1, W2, which is, you wrote down column, V1, W1 plus V2, W2. You see? It's great. It's what Grassmann tried all his life to multiply things together. Here you get a number, but it's a great thing, and that's exactly the scalar product. And so what we know how to do here, is T preserves the structure if and only if V transpose, well, I'll write it down long, V transpose TV, this is television, TV transpose TW, yeah, equals, and now we have to multiply it out. You know what transpose does? It flips the order of everything, right? So that's V transpose T transpose T W equals, doesn't change anything, V transpose W. Right? That's the equation. I just put it in there and did a stupid calculation. It's good sometimes, right, Deepak? Yeah, it's good sometimes. It's good. You sit in the bathtub and you have nothing else to do but enjoy life, and you do a calculation. Yeah, my mother used to do that. So anyway, so I don't have a bathtub. So I do it in the shower. And it's good because I have a sore back. And it's good for my back in the shower. So that says what I have here in the middle, as you can check easily, check it. That means T transpose T is the identity. Yeah. And you can check what that means. It means we have a certain, this means, and you can check this now as a little exercise, that you have, it means that one example of such a thing would be this. Let's check it just for fun. I talked about it yesterday. This has to be an orthogonal transformation. E1 goes to E2 and E2 goes back to E1. It just exchanges the two. And you should get very impatient when you see the determinant of this thing equals -1. You should say, somehow I've reversed orientation because the determinant measures somehow volume or area, and that says that area is more or less the same except I've changed the sign of the area, it's -1. So, but this is certainly an orthogonal group. This is NO2, that's something. And if you look, we talked yesterday, T should be A, B minus B, A. You can check, it's pretty important to check this. This means E1 goes to AB, and E2 goes to minus BA. And the fact that this is minus BA here and here, this means that the image is perpendicular still. So it has to be of that form. And you can just check in this calculation that that's all that it is in that form. Right? So if it's like this, so here the determinant is equal to +1, because we have to have a squared plus b squared equals 1 because length should be preserved. Determinant in this case is +1, determinant this is -1. Okay? So here we go again. Here we go again. Every element of O2 is written as something in O2 plus, and here, well, it's a Q, why did I write Q? It's crazy, Q for crazy. So here, I mean, the determinant of this thing is 1, is plus 1, not minus 1, yeah? That thing here is exactly what I've got here. This is a group of rotations. And then times, maybe times, now we're going to try it again. Let's see if I get it right. Times, yeah, the group of reflections. Yeah? And this group of reflections, I'm going to call it, just for fun, let's call it the group of order 2. C2. C2 is the cyclic group of order 2. Group of order 2. Order is the number of elements in the group. This is given by the identity, and in this case, an element R, which is acting as a rotation, where R squared equals 1. That's the cyclic group of order 2. It's a cyclic group of order 2. Now, everybody in this room had very good lectures from many friends of mine, including from me, right? And you may have seen this notation for this group. So this is acting as a reflection, right? This is acting as this thing. So let me just emphasize here. This is acting as, with this matrix, it's acting as a reflection. Yeah. Sometimes you would see this notation. Yeah? C2. And sometimes you would see this notation. Okay? I know you've seen a little bit about equivalence relations, right? You've seen a little bit about groups, I hope, I think. I, in fact, know, because I asked Kayvon, and I know what I taught people. So this means equal to the integers modulo 2, which means equal to the integers modulo the even integers. Right? And it means in equivalence relation lingo, n is equivalent to m if the difference is even. So n minus n is a multiple of 2, some k. So it's in the even numbers. It's completely clear, I hope, that the integers look like this: 0, 1, 2, and so on, and minus 1, and so on. So 0 and 2 are equivalent, and so on, and so on, and so on, and so on. So you're going to get, this is a group of order 2, yes, with the representatives. Equivalence class of 0 is one representative, it's all the even numbers, and equivalence class of 1, that's all the odd numbers. Right? And then you have fun with your mother at nighttime. You call this thing 0 for that, and you call this thing 1 just for fun, and then you say that 1 plus 1 is 0. So, right, because 1 plus 1 is even, and even numbers are 0 in this discussion, right? Okay. Yeah. Now, I was sitting in a hot tub in Florida in nice weather, and it was vacation for the children from schools nearby, and they visited their grandparents, and they came and sat in the hot tub with me, and I had on a t-shirt that says, of course, 1 plus 1 equals 0. And the children were looking at this, saying, so 1 plus 1 is 0. And this one little girl looked at me and she said, that's wrong. I forgot I had this t-shirt on. And so she's looking at me and said, that's wrong. Okay, so it's really fun. I enjoy talking with these young children. It makes fun. So here's the point. This C2 is generated by a reflection. A thing acting as a reflection. You reflect twice. If you don't believe me, reflect twice. Multiply the two matrices together. Reflect twice. Well, you know, but I'm just going to do the matrix multiplication. Row times column, 1. Row times column, 0. Row times column, 0, 1. It is a statement that a reflection is an element of order 2, right, in this matrix language. So we have a certain group of order 2 in the orthogonal group, and the rest of them have determined it positive. The rest of them are determined either one of the transformation here is in general either an oriented circle or a circle, an oriented rotation, or a rotation times this reflection. That's it. Now, you ask the question, Professor, I don't know who, maybe Søren Petra says, well, what does this symbol mean? And you say, well, it means C2 normalizes the orientation preserving rotation. All right? That's what it means. And now, you can look at space and think about reflections and all of this stuff. But after a while, you get tired of that, and so you say, okay, let's start it. Here's an orientation preserving reflection. Here's an orientation preserving rotation. And now I conjugate it. Now the inverse of this thing is itself, right? So it's easy to do. I conjugate it with this thing. This is really the inverse. And I see what I get. I mean, all I need to do is see what I get. This is why physicists are right. You just do out the calculation, see what you get. So this is 0, 1. Now how do you do this? Let's see here, A, B. So the thing we get here is minus B. And what we get down here is A. And now we get over here A. This is good. And what do we get over here? A. And here we get over here B. And now we do it again, see what happens. We get A. I'm happy we get A. And we get, oh, minus B, it's sensational. And this is really interesting, right? This is really interesting. You conjugate, and now I have to see what happens here. I get B, I hope I get B, and now I had A. And I'm very happy because still A squared plus B squared is 1. So this is some other rotation. So, right? What rotation is it? I don't know, but it's almost the same one. You're going to look at, here's the first rotation I start with, and I conjugate it with a reflection, I get another rotation. Well, you can see this geometric if you want here. This rotation, then you conjugate with the reflection, you can check what you get. But I just did it with matrices. That's the way Deepak would do it. Right? Probably. Or you just say it's obvious. Okay? So it works. It says that this group of order 2 generated by the standard element non-orientation preserving thing normalizes the rotation group, and you get a semi-direct product of the orthogonal group on the 2 plane. Okay? And that means you're big boys and girls. You have said that the isometries of the Euclidean plane are the semi-direct product of the translation group with the orthogonal group, and the orthogonal group is the semi-direct product of the orientation-preserving orthogonal group, the rotations, and reflection. And all of this is completely natural. And that's 2.5 lectures on what is the symmetry. Okay? And I still haven't answered then, what is the symmetry of the group of the square? Okay, so let's answer that question. Yeah, sure.
So now the group of symmetries of the Euclidean space is also a group of symmetry, is part of the group of symmetry of the affine space, right?
Very good. I'm going to repeat what you just said. You should always say the group of symmetries of Euclidean space is a subgroup of the group of symmetries of the affine space.
Okay,
Yeah.
so can we generalize this and say that if we have a space that have structure and other space that have the same structure plus extra structures, so the group of symmetries of the second space is subgroup?
So So what he's saying is, he has a good question, and I'll answer the question. I'll first ask his question. You have two structures on the same set,
Yeah.
okay?
Okay, yeah.
That's okay. Two structures, whatever that means. Let's not be precise. Let's call it structure 1 and structure 2, right? Let us suppose that that structure 1 implies structure 2.
Yeah.
So for example here, the Euclidean structure implies that you have the affine structure,
Exactly.
right?
Yeah.
Then the symmetry group of structure 1 is a subgroup of the symmetry group of structure 2. Yeah. As soon as you formulated the question a little more precisely, you would easily answer it. Yeah. So, but that's exactly what we need to learn how to do. Ask a sort of a nice general question, but then formulate it a little more precisely. We were talking to Jasper a little bit about this today. You have good ideas, and then be able to formulate a little precisely so you can grab it, right? Otherwise, right? Otherwise, it stays at the level of I don't know. Thank you. That's very good. Okay. Okay, so finally, after 2.5 lectures, we can answer the first question. So the first statement is symmetry group, let's say, let G equal the symmetry group of the square in Euclidean space, in Euclidean geometry. That's interesting. And we ask the question, let E2 and E2 equal this E2, let's call it E2R, be the symmetry group of the Euclidean space, which we now know is O2, semi-direct product, this group of order 2, which is generated by a reflection. C2. Oh, no, we're not done yet, I'm sorry. Semi-direct product is terrible. I forgot the translations. Right? I forgot the translation. Yeah? That's okay, but it is clear. So what is G? G is the stabilizer of S in the Euclidean group. We made 2 lectures of an argument.
You forgot to write the plus. Forgot to write the plus.
Your plus here?
Yeah.
No.
Oh,
No, I don't want a plus. The Euclidean isomorphisms. Thank you. Yes, thank you. Plus.
I think it's also the other.
And here, maybe I've forgotten plus, this is O2, if you get something over here or something?
No, it's just the symmetry coordinates in the outward direction. So it's
Absolutely. Absolutely, because this normalizes that. It's good that I make that mistake so that you can correct it now, but no, really, I mean, it's, right, just remember, so this is the whole setup, looks terrible in E2R. So step one, only the zero translation, only 0 in R2 plus, as a translation group, stabilizes the square. No translation stabilizes the square. I think you have to prove it, but you have to define the square precisely and then prove that no translation stabilizes. I think this is clear. Okay. Step two. The stabilizer G is therefore contained in the orthogonal group O2. And O2 is understood very well as a semi-direct product of the rotations with this reflection group of order 2. Step 3, the reflection, so this, let's say, let me make this, let's call this thing that generates this R. Step 3, R actually stabilizes S. Right? So R is a well, if you don't believe me, here is, oh, well, let's even do it with let's do it with numbers. Let's do it, why not with numbers now? Let's call this thing, it doesn't matter, let's call this thing, oh, well, I don't care what I call it. Let's call this thing 0, 0. And then maybe this thing is, I don't know. I don't want to call it anything. So, all right, 0, 0, what is this thing here? Well, maybe this thing is 1, 1, is 1, 1. No, it's 1 minus 1, right? Maybe. And maybe this thing is, then you start putting numbers on this, then you understand it better with numbers. Some people with numbers and some people with letters. Let's see. If that's the case, then this would be minus 1, 1. And this thing would be minus 1, minus 1. You don't need numbers, but it's nice to call them that. Yeah? Why not? And let me see here. Let's say that the reflection, we have to choose which reflection it is. I have to, I've already chosen what it is. The matrix of this reflection is 0, 1, 1, 0. So that means that E1, that means that 1, 0 goes to, what does it go to? 0, 1. And it means that 0, 1 goes to 1, 0. 1, 0. And what does it mean? If 1, 0 goes to 0, 1, and 0, 1 goes to 1, 0, aha! This is a fixed point. You agree? 1, 1 is fixed. I usually look at fixed points first. Isn't it true that 1, 1 is fixed? Because that goes to 0, 1, and this goes to 1, 0, and so 1, 1 goes to 1, 1. That's a fixed point, and I claim minus 1 is also fixed. That is stupid. Because this mapping is linear. This is fixed. So this is happening linearly. So of course this diagonal is stabilized. That's good. And these corners are fixed. So all I need to know is what happens to this point here is, let's see here, the bottom point, let's say the, I don't know, the top point, minus 1, 1. Well, I mean, I know where it goes because 0, 1 goes to 1, 0. Another thing gets flipped over, goes to minus 1. And so the reflection is a reflection on that diagonal. There are two diagonals, of course. It's a reflection on that diagonal. So I could choose the matrix to be this reflection or the other reflection. Right? Okay, so that's what the action of R. So this is action of R. Of R. And that certainly stabilizes the square. So if K times R in the O2 is the decomposition, so I'll write it here, O2 plus semi-direct C2 stabilizes the square. And R stabilizes it, which it does. Then certainly K stabilizes it. All right? K stabilizes it. Think about what you're really using here. So the next step is, which is maybe step 4, what is it? Compute the stabilizer S in the rotation group O2R plus. Okay? All right? So if you have some rotation, let's write it again. Yeah? And you start here, maybe we call this x1. And we start here with x2, and you let's say we rotate it, and we go to x2. Then it's really a rotate about the center point. That means it rotates from there to there. Then that's completely clear that it rotates from there to there, and so on and so forth. So you see that the rotation group acts transitively on the corners, and the elements of the rotation group, here's an element of order 4. We could have an element of order 2, I think, if you rotate 2 angles. So you just take the angles, x1 goes to x3 is a rotation. That's a big rotation. By the way, it's a rotation of 180 degrees, right? Because here's 180 degrees, right? Rotation of 180 degrees. Then that doesn't give them all. So the rotation group part, so K is an element of order 4 or 2 or what? Or 0 or what? I mean, it could be the identity, right? It could do nothing, right? Well, and then you have the matrix of K. And don't forget what the matrix of K looks like. It's A, B, minus B, A. And A squared plus B squared is 1. And another way of saying this is cosine of the angle theta, and this is sine of the angle theta, the rotation. This is what this is on the circle. This is minus the sine of the angle, of course, and this is cosine of the angle. It's a rotation through the angle theta. Well, when a squared plus b squared equals 1, this is sine cosine. And now here, the interesting thing is K of order 4, excuse me, means that theta is pi over 2, right? Because if you have a rotation of order 4, so 4 times pi over 2 is 2 pi. That's a rotation, right? Yes? And the other one is just a subgroup of that. So it says that the stabilizer of this thing is a semi-direct product of the rotation group of order 4, and which is a C4, the cyclic group of order 4. Again, I'm emphasizing in my notation, I don't write Z there, I write the cyclic group of order 4. It's a cycle of order 4. Cyclic group of order 4, semi-direct product, the cyclic group of order 2. Yeah? And everybody in the room believes this is not commutative. Rotations and reflections do not commute. All right? So this is a group of order 4 with this. And so we need to know, this is a reflection, so elements here are pairs, K, R. So this is the reflection generating here, say R. And this is, say, one of the generators of C4. So this is K times R. And now I claim it normalizes that, and you know what it does. It's R, K, R inverse. It's the only possibility for normalizing that is K inverse. It either commutes, which it clearly doesn't, or it normalizes it in some non-trivial way. And the only possible way you could check to normalize that group in some way is by conjugation acting on it by taking it to the inverse. It's a group of order 2, and it only does something of order 2. And that's the only possible thing you can check. Okay? So I've told you what the group structure is of the symmetry group. Let me finish it. It is the semi-direct product of 2 cyclic groups, where the normal group is the cyclic group of order 4, and the action of the cyclic group of order 2 is just by taking an element to its inverse. Yeah.
So the choice of C2, or what we exactly say to be R, is not unique.
Is not unique. That's very good.
So we could take.
That's absolutely right. There are many C2s. It's a very good exercise. Kevin mentioned it. It's right. You just look at all possible subgroups with your group and see what they are.
Yeah.
But as Mr. Weiss was just saying, you could take the other reflection, right? And this would also normalize the rotation group.
All the 2 others or whatever.
Yeah. So you see. So that's okay. So it's a different group, but it's so. The same group can have many representations as a semi-direct product. That's what you're saying.
Yeah.
It's rather interesting, right? So, yeah. And then there's another group of order 2 that's really simple-minded. It's the group of order 2 inside of C4. So it's a group of rotations of 180 degrees. That's a group of order 2, but it's here. Yeah. That's a very interesting thing. So this is the first group that anybody understands in finite group theory, and it has a name, therefore. So the usual thing here is the action of C2 on C4. So rho of K equals RK, R inverse is K to the minus 1. That gives you the group structure of this group. This has a very famous name. It is called the dihedral group. Dihedral group of order 8. And sometimes you see it written as D8, dihedral. And sometimes I get confused. It's sometimes maybe called D4, because as soon as you know what the 4 part of it is, you know what the 2 part of it is. Okay, but I think it's usually called the dihedral group of order 8. It is a symmetry group of the square regarded in Euclidean. So, now I want to continue lecturing a little bit, and then we can go to. Yeah. I think you've learned a lot of concepts and seen the way I think about a lot of things. Okay. So I would like to discuss now what the notion of an orbital group. Well, what is an orbital group and how do we think about it? So we start with a group action on a set. action. And the notation here is G with X down below. This is my notation anyway. This is the orbit. I talked about this a little bit. Is the orbit everything you get by applying G and G. Okay. Now, please, it's the end. You're getting tired, and I'm tired. Everybody's tired. All of God's children are tired. You're not tired. Upvik's not tired. He's fantastic. Yeah, he's a strong guy. Yeah. So I'm not really too tired. When you're tired, let's look at the various orbits. So let's take the example. G is the semi-direct product of is the symmetry group of the square. Of S, the square. Okay? And let's say that C4, we quite often write it this way, is generated by K. So what that means is C4 is the identity K, K squared, and K cubed. And C2 is generated by R, and we just talked about it a bit. Well, it's just generated by R, and that means it's 1R. And the semi-direct product notation simply means that one normalizes the other. It means a general element K times R is a general element of the group. Okay. Good. Now, we're all tired. The first time when you see a group action, you take the group and take a point and ask what its orbits. Okay? So, G of X. So, what is the square? The square is really, what is the square? What do you think the best thing is? What is key for the square? Let's forget the square. Let's let script C be the corners of the square. Okay? X1, X2, X3, X4. Okay? Okay? So let's first start acting. What is G of X1? So the G action on the corners. You're tired, what is it? The G action on the corners.
Just the other corners.
Huh?
I mean, just rotating them and getting the other corners.
Yes. Do you hear what he said? What's the orbit of G at any corner? Every corner. You agree? I mean, so I'm asking such a simple question, you can't believe it. It's completely clear. You even don't need rotations to do this. In fact, C4 of anything is the same. So when you're analyzing a group action, you say G, the full group, and the subgroup, C4, act transitively on the corner. Okay. So G of X equals C for any X. So acts transitively on the corner. What about the rotation group? So then you say, what about the rotation group? The rotation orbits, of the reflection group. Orbits of the reflection group. In this case, it's C2. Okay? What's the orbit of x1? X1. Are you all following this? You're just shy. It's X1. Okay? It's X1. What's the orbit of X2?
X2 and X4.
You got more, I hope, right? What do you get?
X2 and X4.
Kenny? You're right, I'm sure. What?
No, I didn't say.
What's the orbit of X2 by the reflection group?
X2 and X4.
X2 and X4, right? Yes? You get to X2 by doing nothing, and X4. Great. What's the orbit? Great. What's the orbit? Well, okay. We could do them all if you want. What's the orbit of X3? I guess it's a fixed point, right? And the orbit of X4 is X4 and X2. Right? So it really depends on the point. Right? Depending on the subgroup and the point. You just calculate it out. There's nothing to keep going on here. So we've explained all the orbit structure here on this group. I can tell you we are all so tired, I think we should stop now. We should ask questions, unless you want me to go on. We have some time. How tired are you? Normally I would lecture for another quite a while. Should I lecture for another 15 minutes? I'll give it another shot. Okay, it's really hard. Okay, good. So, it's a very interesting thing. I'm looking at a very interesting question. It's an interesting setup here. I'm going to look at an orbit. I'll draw it as a continuum. So here's X, and here is the full orbit GX. And the general element of this thing is G of X. And we have a very special group here, G sub X, which is the set of elements in G which fix X. So these are, the whole orbit is some big thing maybe. You go all over the place maybe with this orbit like we did here in this example. But then you ask what fixes X? That's a key thing. This is a subgroup, obviously, of G. It's completely clear. If G1 fixes X and G2 fixes X, then G1 times G2 fixes X. Completely clear. Right? And now, you see, you have everybody in this room, if you have courage, can now ask the right question. What happens instead of just taking G, let's let H be in the isotropy group here. Okay? Let's let H be in the isotropy group here, and let's look here at G times H of X. Is this picture right? I take two things, just take G, any one of them, and let's take H in the isotropy, and we'll see what happens. Yeah?
Didn't you say it's in the stabilizer? I mean, so the isotropic group is the stabilizer?
I just wrote it here. It's what stabilizes X.
So why do we get two different points?
Yeah, that's you're telling me my picture is wrong.
I mean, it seems
You hear what he's talking about? My picture is wrong. Because if H does nothing, then you first do nothing to X, and then you multiply, you operate on it by G, and you get the same thing, right? So it won't, this is, the right picture is this. This is the same. Okay. It says that the isotropy group Gx operates trivially in this sense. It means, very slowly, what it means is G H of x, is what Mr. Weiss just said, is equal to G of x. It's a stupid remark. It's a stupid remark. It doesn't change anything if H is in the isotropy of x. Right? Okay. Now I'm going to make a mistake, I think. Let's see what happens. So the isotropy acts trivial in that sense. Okay. So let's make a mistake. I think this should be a mistake. Let's try it. Let's try it. Here's the orbit. This is point x. This is the orbit Gx. Element here is Gx. And let's let H be an isotropy at G at x. And that's the same thing as G of H x. So it does, that's the difference in this, the lack of unicity in this discussion is the isotropy. Now let's do it again. Let's take y. You ready? Y. Okay. Well, let's say y goes over here. G of y. And let's see here about, let me make just a question mark here. What about G times H of y? The same thing. Is it the same? Deep back here, shaking your head. No, yes.
No, well, if the isotropy group of y and x is the same, then it's the same.
If y, no, y and x are different.
Yeah.
So if y and x are different, what does that mean at an isotropy level? They may be different, right? So this is not necessarily the same. So you are led, I'm led to answer Deepak's question. I take x and y different. When are the isotropy groups the same? Right? They may or not be the same. Okay? So you're led to Deepak's question. If H is equal to the isotropy group at x, and let's say H hat is the isotropy group at x hat. As Deepak points out, who the devil knows what's going on here? Let's figure it out. Okay, so let's figure out how these things are, and let's assume x hat is equal to G of x in the orbit. So I'm over here in the orbit. I have x, and I have x hat, and that's equal to g of x. And we want to know what the isotropic group is here. Okay? Well, let's see what happens here. How do I get something that fixes something here? Well, let me see here. There you are, he's always going to Fegezak, I know. Yes. If you want, here is Jacobs University. That's G of X, that's you coming from Fegezak. Right? Here you went from Fegezak to this is Fegezak. It's X, but it's really Fegezak. And here you are. No, here is Jacobs University, and here you are in Fegezak. Let's do it that way. Okay. And how do you go back? Here's Fegezak, and here's Jacobs. And what you do to get isotropy, you walk back or take the bus from, he takes the bus, I saw, because last year you always taking the bus. I take the bus too. So you walk back from Fegezak to Jacobs, you fix Jacobs, right? You smoke a cigar and drink cognac, and then but you fix Jacobs, and then you go back again. What have you done? You walk to Jacobs, you do nothing, you screw around and do nothing, and then you walk back. The end effect of that is doing nothing. Right? I hope you see that a trivial calculation says the isotropic group at G hat is, well, first you walk back to Jacobs, then you do nothing at Jacobs, and then you walk back. Isn't that true? Isn't it true? If you get anything from this lecture, you get the lecture that conjugation action is extremely important. Because you see how the isotropic groups vary in an orbit. They're different. They vary in an orbit. So as you move along the orbit, the isotropic groups are conjugated. As you move along the orbit, the isotropic groups are conjugated. Now, what happens if the isotropic groups, what does it mean that the isotropic groups are the same along the orbit, that they don't change? In the lingo of group theory, if the isotropic group, so the isotropic groups don't change, along an orbit, don't change, let's call it the isotropic groups Gx, G sub x don't change, don't vary as a function of, don't vary along the orbit. If and only if, you tell me,
They are normal.
they're normal. Remember the definition? Normal? It means conjugation stables all of that. It means the normalizer of the form. If and only if they're normal. Is normal, and now I will give you the new notation. This is the notation the group theory people like. This means that Gx is normal in X. Okay. That is the meaning of normality. Two meanings. If you learn anything from this lecture, it is normal means in semi-direct products that you can really make semi-direct products. I'm pointing to the board here where I was talking about semi-direct products a little while ago. Optics looking at the board, there's nothing to look at because I erased it already. But you know what I mean. Normal is the key. Something normalizes something else means I can make the semi-direct product. Right? The key thing is that isotropic groups don't change along an orbit, if and only if this group is really normal. Okay? And this is the meaning of normality. So you see two meanings of normality. In group theory is one, isotropic groups don't change. Don't vary. And possibility of semi-direct product. Okay? That's what we talked about. Now, if you're a good mathematician, and I hope you all become really good mathematicians, you're just starting out. You heard me lecture about semi-direct products, the role of normality, and so on. You would ask the following question. Suppose n is normal in G. So this means it's a normal subgroup of G. Does this imply that G is a semi-direct product? And what I mean by that is G equals some other group, I don't know, some complementary group, H, semi-direct product, N. You get it? You have something like the translations. There's some question whether, and that's normal in the full group, is a question of whether you have a semi-direct product going on. Right. You should ask this question, right? What is just your guess off your top of your head? What do you guess? Just because I asked the question, guess.
Yes.
He guesses yes. Anybody else to guess? I'll pick. You guess yes or no?
I say no.
You say no. This is democratic here. Okay. The question is, given a normal subgroup, can you find a complementary group somehow to make this product structure, right? And so you should look at the first example in life. Look at the cyclic group of order 2, order 4. The cyclic group of order 4. Yeah? Let's see what this group is. Let's see this is a group 1, K squared, K cubed. This group is abusing. It commutes. Every subgroup is normal. I mean, this is a triviality. Every subgroup is normal. All right? And now I'm going to take, this is G. And now I'm going to take N to be the copy of C2 in here, which is generated by that guy in the middle, this group of order 2. Okay? Okay, you see what I'm saying? You take the group of order 2 inside the group of order 4, and everything's commutative, so everything's normal. Is that a semi-direct product? Or can you find a complement of the group of order 2 in there? Complement. What's the complement of the group of order 2 in here? Can you find it somehow? What if K is in the complement? You get everything. It's a generator. What if K cubed is in the complement? You get everything. It's a generator. Okay? So you're right. The answer is no. It is a very non-trivial, important question. Given a normal subgroup, does the group split as a semi-direct product? Right? That's the question here. Given a normal subgroup, does the group split as a semi-direct product? Okay. The answer, you were optimistic, is okay. But it's a very, very interesting question. Okay? And if you get interested in that question as an algebraic question, We could talk to me and I'll tell you some nice examples and you can write a little paper about this subject. So get interested in some examples, come to me and I'll tell you interesting topics to write on the paper, and I'll also send some around in the works and so on. Okay? Good. Any questions now? I don't think so. We're all tired, so see you tomorrow. Thank you.